for those of you who are here for the first time, you've not heard this before, but the Simons Institute was founded by a generous grant from the Simons Foundation in 2012, and it continues to sustain us to this day. So we're able to bring together, people for sustained collaborations over a semester in length. It's the only place that does that for all of computer science. I don't believe that there's any area of computer science where we have a system where we bring people together for an entire semester. Because our focus is theoretical computer science, so we want to understand the nature of computation and new computational models and so on. But we're always looking for the theoretical lens or the algorithmic lens on other areas. And for the last couple of years, especially this year, the focus has been on machine learning, large language models, artificial intelligence in general. These areas were very close to theory once upon a time, and we're trying to regain that proximity again. And it's at the right time to do this. And I'd like to thank the organizers of this workshop, putting together a very exciting workshop on transformers. I am particularly excited to hear about the connections between transformers and complexity theory and the view of transformers as a computational model and so on. So I'm looking forward to that. A few bookkeeping remarks before I hand off to Surbi, one of the main organizers, housekeeping remarks. This auditorium allows no food or drink. So you're not supposed to bring food and drink into the auditorium. If you've done it this time, you didn't know that's allowed, but please don't do it again. Water is allowed. Another request I have is that the staff work a lot in putting together workshops and making sure that things run well. But they're doing this all the time. So they would like to be done by 5 p.m. when the workshop ends. So if you want to continue your conversations, which often happens, please do so in the area outside the auditorium and not in the auditorium. The last thing is, if you're going to lunch and want to protect your valuables, there are lockers available near the restrooms where you can store your backpacks for the day. Okay, have a great workshop. Here's Suri.
Thank you all for being here. This is a workshop which the title is Transformers in the Computation Model. It's part of the special year on large language models and transformers, and one of 4 workshops that we'll have. This is the very first. First, I'd just like to put a shout out to all the organizers. That's me, Surbi, Jacob here, Ravi is there in the back, and you'll see Jacob Steinhardt also around during the workshop. And of course, the entire Simon staff for helping us put this together. Well, I'll start with explaining what the goal is. That this is the thing we started with. This is attention, all you need. And this is actually the slide that Jacob made, so he's going to talk about it.
Okay, yeah, so just, wanted to sort of put this up here. This is a bet between Jonathan Frankel and Sasha Resch, who's helping organize the LLMs program this year. And I think the sort of context in which this workshop is taking place, right, is that we have LLMs doing all of the impressive things that LLMs have done. It feels like the rate at which progress in sort of ML, especially applied to language, is happening is incredibly fast, is maybe getting faster and faster every year. At the same time, we are using essentially the same basic model architecture that we were using back in 2017 when this Transformers paper first came out. And so I think there's a lot of sort of deep and interesting questions about what does this mean? What does this tell us about language? What does this tell us about this weird specific computational model that we've settled on as the foundation for all of our language models? What does this tell us just about sort of AI in general? And I think those are the kinds of questions that we're hoping to get at over the course of this week. And so one of the things that I'm super excited about is that we are bringing together here people from a bunch of different communities. As some of them were saying before, there are sort of people from the NLP world and people from the complexity world and people already doing interesting work at the intersections of those things, and people who are building and deploying sort of real versions of these models out there in the world. People from that ML theory background that used to give us more structure, more idea about what to expect from our models once upon a time. So, maybe the main thing that I want to encourage everyone to do here, in addition to just watching all of the talks, is to talk to the other people around you. At the kickoff for the generalization workshop, Matus asked people in the room to raise their hand if they identified as applications people, and it was just me and Unsel Choi, and we were these sort of weird creatures. And now you're surrounded by, applications people and theory people and everything in between. So, please do take advantage of the other people around you. But yeah, I think the sort of high-level questions, the high-level themes here are both, while we're at a sort of theory-focused venue, can we explain theoretically the effectiveness of this specific transformer architecture on the various things that it's used for, both in building AI systems that process language, now in vision, now in computational biology, now in physics applications as well, and all these other places. Can we maybe take insights from theory to predict what the limitations of this modeling paradigm that we live in right now are going to be, and what to expect in the future, and maybe most importantly, how do we sort of motivate or design the next generation of models that we're going to be using. So with that, we'll hand it back to Sylvie.
So just to tell you about the events that we have planned, we have a bunch of invited talks. We have roughly 4 to 5 talks every day. They're scheduled to be 45 minutes with 15 minutes of discussion time during the break. So we would encourage you to talk to the speaker. Also post a session on Wednesday from 3 to 5 p.m. We've selected a really nice collection of posters from students and postdocs and other people who submitted. So that's going to be on Wednesday. I'll tell you the room number. We're also going to have 2 panels. The first panel is going to be on the question that all of us are somewhat asking, and what the point of this workshop is. What can theory offer to the design and use of LLMs? And the second panel will be more getting a perspective of whether these transformers are the end game and what are the post-transformer architectures and other models that are interesting. We also have a hike on Friday. This is just something so that we can explore Berkeley and actually talk and discuss in a more relaxed environment. And that's what we'll end the workshop with. Here is a QR code for the Slido to put questions for the panel. I would encourage you to please add questions during the workshop, whatever comes to your mind when you're listening to the talks. And we try to incorporate them in whichever panel they make sense. With that, we'll start our workshop. We have our first speaker, Daniel Shu. Daniel is an associate professor at Columbia, and he has been working a lot on the foundations of machine learning and statistics before this. And in the last 2 years, he's done phenomenal work in trying to understand the representation and limitations of transformers, and that's what he's going to present today. I'll take it away.
Thanks. Okay, thanks for an introduction, and thanks everyone for being here. So yes, I wanted to tell you about some work that we've been doing over the past couple of years on trying to understand transformers. Just say that I've only kind of learned about transformers maybe 2 years ago when Matus kind of started telling me about these things. So this is kind of our journey over the past 2 years. This is of course joint work with my PhD student, or former PhD student, Clayton Sanford, who's now at Google Research and Matus. So our high-level motivation is to, from very broad, high-level perspective, is to try to put transformers on kind of firmer mathematical footing. And to do this, we hope that we should at least be able to explain what's kind of distinguishing features there are of transformers that are important as compared to other kind of neural architectures. So here, kind of a depiction of a recurrent neural network, which kind of was a model that dominated people's minds in kind of the early 2010s, I guess, for language modeling. And yeah, somehow, like as Jacob said, that in 2017, everything kind of shifted over to this transformer architecture. And this is, not, with the hope that there is something interesting to define here, because there are a lot of these benchmarks that people have been doing over the past several years. This is a figure from this kind of scaling laws paper that really do show some striking differences between the performance of other architectures like LSTM, which is kind of some variant of recurrent neural networks, and transformers, especially as they scale, as you're applying them to larger and larger data. So here, the x-axis is the number of tokens, or think of them as words, and in the context of a transformer, and the y-axis is the kind of the prediction loss. How well are you able to predict the next token? Lower is better, and it's kind of clear that there's a remarkable difference between the performance of transformers compared to RNNs, and the kind of difference different widens is kind of not so easy to see, but the different widens as you kind of make the architecture bigger and bigger. So somehow like high-level goal is to try to compare different models, and there's a lot of things and ways in which you might compare different models. There's a lot of aspects of a model that contribute to its success. There's of course the representational power, which is what I think a lot of people have been focusing on in recent years. There's kind of the complexity of using these models, the complexity of the inference task of using models. And of course, from machine learning, it's very important to understand the learnability, especially nowadays with particular training algorithms, like stochastic gradient descent, and many others. So these are different factors in which might contribute to the success of a model. But how do we compare these things across models? Not so easy, I think. So one, you might compare like parameter count. So one parameter for a transformer had with the exchange rate of a transformer parameter to an RNN parameter. Maybe not so clear. Inference time, well, maybe it depends on the hardware or the mode in which you're using these models. Again, not so clear. And data efficiency, of course, is the kind of machine learning aspect of it. How well are these things, how well are you able to train these models to use data in the most efficient way? Again, this is also very not clear. So what I'm trying to do in this talk is just to focus on one very kind of narrow aspect of one way of measuring the performance of these models and maybe some comparisons, which is to focus on what you can represent with very small sized models. And in particular, what capabilities are enabled by this feature of parallelism that transformers seem to have. And this is something that I think other people will touch on in this workshop. So there's a very nice work by Greenban and Sergey and others, and Will and Ashit, that focus on other aspects of parallelism and how they are related to transformers. And so this talk will be kind of complementary to those. So good. So that's the kind of the setup for the talk. Here's the plan for what I'll talk about. I'll first start off actually talking about the role of depth in transformers, especially in the context of induction heads or in context learning. And then I'll try to draw this connection between transformers and a particular model of parallel computation, which is this massively parallel computation model. And then I'll close out with talking about some limitations that other architectures seem to have. It's okay if I don't get to all those. I might not get to the last couple of sections, so feel free to ask questions throughout the talk. There's like a version of this talk that was given at this Plan seminars. So if you want more details, feel free to check out that talk. Any questions before I get started? Okay, so I want to first talk about the role of depth in transformers in the context of induction heads. Let me first kind of remind you, probably for this audience, this is hopefully there's a reminder, and also if you've seen the bootcamp talks for this program, this should be kind of just a refresher. So we're talking about transformers, and kind of the underlying building blocks of transformers is this so-called self-attention head. So what does a self-attention head do? It's some mechanism that processes n tokens, call them x1 through xn, and outputs a sequence of n output vectors, which I'll call y1 through yn. So how does it do this? So the first thing that it'll do, or the first way to think about it is that the first thing that happens is that every input token, x1 through xn, each one, and from each one you generate 3 different vectors, a query vector, a key vector, and a value vector. This is done independently for every input token. And then we're going to compute the n different outputs. So the ith output, yi, is going to be some convex combination of the n different value vectors. And the way you combine these, form this convex combination, form the coefficients, is that you take this so-called softmax between the ith query and the jth key. And that's going to be the weight that you assign to the jth value for the ith output. Okay, so the first thing I should say that the way that the first step happens is through some multi-layer perceptron. These are what's called the token embeddings. You take some tokens, which might be vectors already, and they might just be symbols. You somehow have to create vectors out of these things, and this is done using kind of more classical neural network architectures. But kind of the magic of self-attention is that when you were, each output potentially depends on all of the input tokens through this convex combination. And the weights that you assign are just given through the softmax transformation. And you have this kind of softmax weight kind of reflecting how much the ith token should care about each of the each of the n possible other tokens. And kind of importantly for in the context of this talk is that each of these outputs, all of these outputs can be produced in parallel. Right? You can produce each one separately, independently of all the other outputs. Okay, so hopefully this is just like a refresher for everyone. It's not so important. I'm not going to get into much detail about the specifics of how self-attention works, but maybe it's good to keep in mind. So that's the self-attention head. That's just the basic building block of the transformer. But what is a transformer? It's really a composition of these things. So a transformer is the composition of potentially maybe like a sum of a bunch of these self-attention heads. You may sum up a bunch of self-attention heads, but then compose that with another layer, which is a sum of self-attention heads. So what really happens in a transformer is that you start with some sequence of tokens, like let's say words in this case, and then you apply some layer, maybe a single self-attention head or a bunch of self-attention heads, and then you create another sequence with this kind of some vectors, one corresponds to each input token. And then maybe you apply another layer of self-attention heads, and that creates another sequence of vectors, and so on and so forth. And so you might ask, well, why do we need multiple layers? Why do we really need to do these things in this kind of stages rather than just all one go? Okay, every token already can look at all the other input tokens. Potentially, you could just shortcut everything, just immediately compute what you want for the output. Okay. So not clear exactly why it's necessary. So what people have found is that somehow the role of depth in transformers seems to be kind of tied with this kind of amazing phenomenon or capability of transformers in large language models that's called in-context learning. So this is one way that you can think about what in-context learning is. You give a transformer a bunch of examples of input-output pairs. So this is presented in the context. So here, the input-output pairs are just a little snippet of text, and whether it's a positive or negative sentiment. Another snippet of text, whether it's a positive or neutral sentiment. Another one, and then you prompt it. And then the final thing is another sentence whose sentiment you want to predict. And you ask the language model to predict the next token. And in this case, it'll predict a positive, which seems reasonable in that case. And so somehow the idea is that somehow just through the inference process of the transformer, it has processed all this context, and using more context this way, it's able to better predict what this next token should be. And kind of the amazing thing is that this is not specific to any individual task. In fact, you just change the label here, trying to predict the sentiment of the sentence. You predict the category, the topic of the sentence. The language model knows to kind of predict as the next token the topic instead. Okay, this is the phenomenon of in-context learning. I'm not going to get into any details about exactly how this works, but what people from Anthropic, the researchers at Anthropic have kind of identified that kind of the basic mechanism behind in-context learning is something that they call the induction head. Okay. So here's going to try to give you their example of how to think about what an induction head is. So here's a potential prompt that you might feed to a large language model, which is just the first couple of sentences of Harry Potter. This is after you tokenize the words. So this is the sequence, and then you ask the language model to predict what comes with the next token here. And the way they kind of explain how language models does this is that, well, it looks at the latest token and finds what's the latest previous occurrence of this token in the context, which is here, and then just output whatever followed that occurrence, which is this token, LEY. So they abstracted this, kind of found that this structure, this kind of kind of algorithmic sub-circuit kind of occurs in a lot of these two-layer transformers that they train on large corpuses of text, and they call this an induction head. So here maybe a way to abstract out exactly what that functionality is. You're given a sequence of tokens, and the ith output is supposed to be, the way you compute the ith output is that you look for the last position previous to the ith position where the ith token occurs. So then maybe that token, ith token is A, the last time you saw an A is at position J, and just output whatever came next. So the definition of induction head here for people. Okay, so this seems to be something that apparently transformer is able to do. In fact, formalize exactly how this is done. So here I cited a very nice paper where I first learned about this by Alberto and others. Maybe I should actually cite gradient descent, because gradient descent also found this just by training on text. But here's one way that it might happen. It would be kind of a two-stage process. Okay, so this will be implemented by two self-attention heads, composed with each other. So the first layer, something very basic happened, very, very simple, that every token kind of attends to, well, itself, kind of its own position and the previous position. And then you just copy the key of the previous position token to your current position. So that's the first self-attention head. That's something that turned out to be easy to implement using a self-attention head. And in the second layer, you now just issue the query. Now you're kind of trying to query, where's the last time I saw this particular token A? Well, I match it with the key that got passed from the previous token. So now it's attending to this position J plus 1. And now it knows that I should predict B at the output. Okay, so this happened with two self-attention heads. And you can ask, well, okay, why do we really need two self-attention heads to do this? Turns out this is something that you can mathematically prove that you cannot do this really with one self-attention head, okay, or even just one layer of self-attention heads. This really is kind of fundamentally a two-stage process for self-attention. This is a theorem that Clayton and Matus and I wrote down recently. Here's the kind of the formal statement that if you have a single layer of, let's say, potentially many self-attention heads, H self-attention heads, and they all use this token embeddings of some dimension D. In order for a single layer to do this, these quantities had better be really large, kind of growing with the sequence length n. Okay. So remember, n is something that you're trying to make as big as possible to make in context learning work better and better. So this is thousands, potentially millions. We're not scaling up the number of self-attention heads or the embedding dimension quite so rapidly. So the way to think about this is that, well, unless we were creating much larger transformers than we are currently, there's no chance that we're going to be able to create, get these induction heads out of single layer transformers. We really do need at least 2 layers of transformers or self-attention to do this. This is something that's been corroborated in empirical findings. So the original studies by Anthropic kind of heuristically argued why you should need 2 layers. Alberto and others also empirically found that it was really hard to get 1-layer transformers to succeed in the task where induction heads are needed. But 2 layers were just fine.
Just for comparison, how many self-attention heads are you using in the 2-layer solution you gave earlier?
That's a good question. It's just one per layer.
Oh, that's cool.
Yeah, and I didn't say this, but I say small here, and so by small I mean that the embedding dimension is also rather small, maybe log n. Yeah, that's a good question. Thanks. Oh yeah, I have all these footnotes that for like the experts, maybe this is important. But I'm not going to read them out. Okay, so that's at least suggests that 2-layer transformers are needed, but clearly we're not stuck at 2-layer transformers in large language models. We're really using many more layers in these language models. So why is this the case? Well, one reason might be that, well, we just need more layers to do some kind of mundane processing, kind of, we have already tokenized these words so that they're kind of split apart. Maybe some of the layers need to kind of like put them back together, or at least put the information back together. Okay, so maybe that's not very interesting, but maybe that's not the kind of like the higher level reason why multiple layers beyond 2 are necessary. So here's one attempt to try to say something about why you might go beyond just 2 layers. So let's again think of a very basic task, kind of like induction heads task. So here's a very simple sequence of tokens, 10 tokens here. So if you were to ask, in terms of the induction heads task, the next token, how would you predict what the next token should be? Well, you would look at the last token, it was A, and then you say, where's the last time I saw an A? It was over here, and with the token followed that, it was a B. So in this case, the induction head would output B as the prediction of the next token.
Sorry if this is a silly question, because from my understanding, the positional information is embedded, it doesn't know that this is the previous token versus what is the first token? It has a positional encoding.
Yeah, it has some positional information there.
Why is it learning to do the previous one as opposed to the very first instance?
Okay, the good question again. Why is it doing this? That I don't know. But suppose you wanted to do this, then I've explained how it might do that. Why would it do this? I think that's a great question. Empirically, why is this kind of important? Well, one answer may be that, well, if that was done in these kind of mechanistic interpretability studies by Anthropic, they found that, well, if you didn't have these induction heads in the language model, the ability to do in-context learning would drop dramatically. Something else would have worked, I don't know. Yeah, that's a great question. This I'm not trying to explain why, but I'm just saying how. Okay, so this is what you would do for induction head. But suppose you can kind of iterate this process. So we made up this task that we call the 2-hop induction head, which is, okay, let's just kind of apply the induction head process again to this token, to this kind of prefix of the sequence. So what's the last time I saw B? It was over here, so maybe I should predict C. So that would be the corresponding output for the next token for this entire sequence. So this is kind of like a pointer following task where you kind of think of kind of following 2 pointers now to predict your output. And why would this be important? Again, not totally clear, but there was a nice paper that Binghui and others and Christos kind of presented in the context of a kind of reasoning problem that they called a function composition problem, or you could think of it as a multi-step reasoning problem. It's a very basic kind of word puzzle that you can imagine. So here, the word puzzle is that you give list out a bunch of people's professions in this way. Jane is a teacher, Helen is a doctor, and so on. And then you start listing who is whose mother. So the mother of John is Helen, the mother of Charlotte is Eve, and so on. You have a bunch of these. And at the very end, you ask for the profession of John's mother. Okay. So this seems to naturally have this kind of 2-step reasoning process. You have to first look up who is John's mother. Okay, and that is, you go here and find out it's Helen. And then you again have to look up what's the profession of Helen. And this is, you have to go further back in the sequence and find a Helen's a doctor. That's how you would predict that Helen's a doctor. So this is the multi-step reasoning process, and it kind of naturally corresponds after some massaging of the text to this 2-hop induction head task. Okay, so can transformers do this? Well, perhaps not surprisingly, yes. Kind of the key thing that's happening is that you're able to solve the 1-hop, the basic induction heads task, for all of the positions simultaneously in the first 2 layers. don't worry about the details here. Just trust me that this, this was the output of the, the correct output for the last input, but these are also the correct outputs for all the previous inputs as well. You can do all of these things simultaneously in just 2 layers. Okay, you don't just compute this one, but you compute all of them. Some of them don't have an answer because you didn't see it previously in the sequence. And then just in one additional layer, you can kind of complete the second pointer following step. Okay, so that's this 2-hop task, the kind of an iterated version of the induction heads. And so this maybe suggests that, okay, well, if with a third layer, we can do this kind of 2-step reasoning task. Maybe we can try to do many more steps, k steps of reasoning with k layers. Okay? And it turns out that you can do much better than using k layers. You can just do logarithmic in k layers. Okay? So I think we managed to get it all the way down to 2 plus like the ceiling of log 2k layers transformers to implement this kind of k-step version of this induction heads task. I don't think this is terribly surprising. This is actually some very similar kind of strategies worked out in a paper with Serby and Bingben. But the basic idea is that every additional layer doesn't just increase the reach of your pointer following by 1, but actually doubles the reach. Okay. I think what's more surprising is that SGD is also able to find this solution when you kind of work hard enough at training it. Okay, so I said put kind of ... here because we can also, in some sense, say that this is nearly optimal, at least under a plausible conjecture about massively parallel computation. Under some conjecture that people in this community have made, you really do need logarithmic and k layers, at least if you're not trying to make the transformer enormous. Okay. So I'm going to next talk about this MPC model, but this is kind of what we've been able to understand in terms of the role of depth in these transformer architectures. Okay. Any questions before I move on to the next part? Yeah.
This is a question in slide 14, I guess.
Sorry.
14? 14 slides.
14. You want to go back to slide 14? Yes.
Yeah, this is finding that it says you can only replicate around the length of n with n layers, similar to that slide. But I just did a quick experiment. I asked it to repeat like 1,000 lengths of character, but it can do the perfect with GPT-4. But the common layer is only around 30 or. Yes, I'm just wondering why it's happening. It's
yeah, I don't know.
Yeah.
Anyone have a conjecture about this?
This theorem is only 1 layer, right?
This is about 1 layer.
Oh, I see. It's not edge. Oh, it's a head number.
Yeah. So once we have 2 layers, we already know we can solve this task perfectly.
I see.
Okay. Good. Any other questions before I go on to talking about MPC?
Yeah. In your construction, how many hits do you have? Is it the number of hit scale with K, or is it?
It's again 1 head per layer, so log K heads.
I had one question. When you have, I guess, the task solving the K reasoning step problems, is that still possible with log K layers with the causal attention maps?
Yeah, so this one it is using causal attention, because you can see the way that even this works, you only depend on the previous, the task itself is causal. So even with causal masking, this is fine.
So I appreciate the footnotes, but I have one kind of detailed question. So you have the model dimension and the vocab size growing slightly with n here. How uniform is this construction? Like how much does it change as the n gets bigger?
All of our constructions are non-uniform.
Okay.
Yeah, that depend. We kind of hard code in the max sequence line.
I see.
for the experts out there, none of what I say is necessarily uniform at all. Whatever that means. Okay, good. So I kind of ended by saying that maybe this construction is optimal in terms of number of layers under a plausible conjecture about massively parallel computation. Let me say a little bit about that. We kind of stumbled upon this connection mainly by looking at pictures and seeing that the pictures look the same. But I think it's kind of a very interesting connection, a different way to think about kind of complementary to the different circuit complexity view of transformers. So what is MPC, massively parallel computation? So it kind of started with this framework for doing large-scale data processing called MapReduce from Google, like I guess 2 decades ago or so. This was like enormously successful. People made open source versions of it, like Hadoop. This was used all over the place, including at Yahoo. And then people at Yahoo, the theoreticians at Yahoo, along with Howard, decided, well, we should study this as a computational model. So they created a formal computational model to study what can you do in this MapReduce or Hadoop framework. And the model MPC is kind of what eventually came out of this this development. Okay. A lot of sequence of papers that really came to the final version of what we call MPC. So I'm not an expert in MPC, but let me just give my best attempt to explain what it is. Okay, so it's a model for trying to process huge data. Okay, so you have input sizes that are really big. You should think of n as really big, and words. You have large number of machines, but each machine, no machine is able to kind of handle the entire input. Okay, so they have some memory size s, and s is sublinear, right? Like maybe like n to the delta for some really small delta. Think of delta as like 0.001. Okay, so they have very small memory. You cannot possibly fit the entire input into a single machine, so they better work together to solve some problem. So what happens? So you have some really big data. The data gets split apart and given to all of the machines. Okay. And then these local machines, they need to kind of do some local processing and some local communication. Okay, so they need to talk to each other. So we're going to send messages. This is what's called the shuffle operation in MPC. And then once they send messages, there'll be a round of computation. They just kind of work on their local memory, doing some computation locally. Okay, so there's some constraints though. So there's communication constraints in the shuffle round. So every machine can send at most s words of total s words to it doesn't have to be like one word to s machines or s words to one machine, okay. Which makes sense because this is how much information you have. And then each machine can receive at most s words. Again, you only have s words of memory, so you should not get more messages than this. So these are the constraints in the communication. And what's kind of interesting in this model is that you just ignore the computational complexity of what happens locally. So each machine can just do unbounded computation on its local memory in the computation rounds. So the main thing to study here is how many rounds do you need of interchanging communication and computation in order to solve some computational problem. Okay, so this is, of course, like a very well-studied field in theoretical computer science. There's books about this. There's all sorts of algorithms people have designed in this model. So if you want to broadcast a message to everyone else, you can do this in a single, okay, not a single, but a constant number of rounds. Okay. Sorting can be done in a constant number of rounds. This is something, that deviates from more classical models of parallel computation, which should take like logarithmic number of rounds. Here, because the memory sizes are a bit bigger, you could do it much more efficiently. Prefix sum, I don't remember what that is, but a bunch of other problems, like problems that you study in algorithms classes, finding connected components, finding minimum spanning force. At least for input sizes to have, input graph to have small diameter, these are very efficient. What's not known, for example, is, which will be important later, is whether you can beat the kind of more classical round complexity for doing connectivity. Classically, you can do this in log n rounds. Not known whether in MPC, whether this MPC model gives you better round complexity than a standard model. Okay, so I don't want to dwell on what this is because I'm not really an expert in MPC, but what we were able to do is to kind of show some relationship between MPC and transformers. So I wrote down the entire theorem here, but just for the experts, but the kind of the punchline, first theorem that we proved, it's basically like a compiler for MPC protocols to the transformer architecture. You can take an MPC protocol in some source code and compile it down to a transformer, and it roughly preserves the round complexity and the space and size complexities. Okay. So the upshot here is that a problem that's easy for MPC is also going to be easy for transformers. Okay. There's one important difference, which I'll get to at the end, which is that here we're thinking about transformers where the token embedding dimension is quite a bit larger than what we were talking about in the first part of the talk. So before we were thinking about maybe log n dimension vector token embeddings, here is more like n to the 0.001 or 0.004 or something.
The key query functions, I guess, here are somehow like arbitrary, right? Like they're not linear somehow. They'll come from the protocol, I guess.
Yeah. So those things in the MPC protocol, I guess you just technically specify what the machines do locally. Here we're going to assume that those things can be carried out by some multi-layer perceptron. Perceptron. Yeah.
How much of a restriction is it to require a causal mask here? Like, it seems like a major difference between this and the standard MPC setup is that everyone's pretty concerned, at least,
Here for this kind of compilation, it doesn't make sense because we're not restricting who can talk to who in MPC. So if you don't have like an ordering over your machines, then we may not be able to do this with causal masking. I'm not suggesting anyone go out and like start hand programming transformers this way, but just kind of a proof of concept.
So should we think of one machine in MPC as one attention head in transformer here? So where's the correspondence?
The correspondence is a little bit different. It's actually more like the tokens themselves are the machines. And a self-attention head is like the routing protocol for telling machines how to talk to each other.
Thank you.
Okay, so the main punchline here is just tasks that are easy for MPC or easy for transformers, and we kind of have a loose counterpart to this, which is basically, okay, probably what this is probably known before in the sense that probably people thought about how to implement transformers on parallel systems. Indeed, this is all we've done in this theorem. But the way we interpret it is that, well, since a transformer can be simulated in this kind of massively parallel computation environment, things that should not be solvable or efficiently solvable by parallel computing, they should also not be implementable by transformers efficiently. So the way we think here is that things that are hard for MPC are also going to be hard for transformers. Okay, so then, naturally you ask what is hard for transformers, and then you go to your colleague Alex Andoni. He tells you, okay, it's this problem. He said, okay, even this problem seems to be very hard for MPC. So it's the problem, you're giving two possible graphs. Okay, you promise it's only going to be two possible graphs. Okay, you only have to work for these two possible inputs. Either it's a cycle on n vertices, or it's a union of two cycles, okay, and over two vertices each. And your task is to decide which one is which. Like, is it the first one or the second one? Okay. Apparently, this is the hard problem for MPC, in the sense that if you want like a scalable MPC algorithm, one that really works with sublinear space, local space, and number of machines, it's only polynomial in the size of the graph, then you really do need log n rounds. We're not going to hope to really beat like PRAM computation with MPC in this case. This is a hypothesis. It's not proven. But if you accept this hypothesis, this conjecture, then this is how we can derive the optimality of our current construction for this k-hop induction hedge task using only log k layers. Beating that would kind of imply that you could do this, violate this hypothesis.
One could imagine reasoning about all this in a slightly different way of saying, look, here's a parallel algorithm for transformers. There's a conjecture that 1 versus 2 cycle problem, there's no parallel algorithm. Therefore, right, that would have been the direct way of doing it. So was there a reason? Was there something more you got out of going through this MPC?
I think it was mainly that that we had this other. Okay, there's kind of two things. One, we wanted to really abstract out what the token embedding architectures are doing, which kind of corresponds to being able to do potentially large amounts of computation locally in a single machine in the MPC model. That seems to be different from how we normally think about other kinds of like parallel architectures. You're not using arbitrary computation on such large memory sizes. I think it was mainly that we saw this, this seemingly bidirectional relationship between MPC and transformers, and so this is kind of the direct way that we saw this.
You mentioned that there's a token to machine correspondence, and in MapReduce there is this key value area, right? The set of correspondence with the keys and values in the transformer and the key value.
Yeah, I don't remember exactly how the key and value thing works in MapReduce, but I suspect there's something similar going on here. I just don't remember exactly the how those are used in the MapReduce shuffle. Okay. Good. So that's all I really wanted to say about MPC.
Isn't there something fundamentally different though? So the MapReduce shuffle doesn't require n squared complexity to do this matching of every query against every key.
Yeah.
So where does that?
Yeah. So that I kind of glossed over here. Here, of course, the in order to simulate the n squared computation that in self-attention, we do need to kind of pretend you have many more machines than n machines. We need n squared machines. Somehow n squared machines are taking care of like the n squared work that you need to, at least that we think we need to do with self-attention. I'll come back to this actually. It's an important point. Yeah.
How would you input that graph to your transformer?
Sorry.
So you have these two graphs, and you want to detect whether it has 1 or 2 cycles, right? Mm-hmm. How are you able to like input that to your transformer?
How do we do this in a transformer?
How would you input that graph to your transformer?
Oh, how do you input? I think there's a lot of different ways you can do this. One is you just pretend every edge is a token. So there's sparse graphs, so roughly n input token. Okay. So finally, I want to just kind of say a few words about how other architectures might stack up. And unfortunately, I started off the talk by saying it is kind of hard, I think, to compare different neural architectures just because it's not exactly clear how one resource in one architecture, how you compare that to another resource in another architecture. We're going to try. Jonah already brought up this. One reason we might want to start looking at other architectures. One is to settle the bet from between Sasha and Jonathan. But another reason is that this kind of quadratic computation that's happening in self-attention seems very, very expensive and seems also hard to avoid without in full generality. And so what a lot of people are thinking about is how to kind of beat the sub-quadratic bottleneck. Right, whether they're just completely different architectures or they're approximations to self-attention that can avoid this computational cost. And so a natural thing you might start, go all the way back to recurrent neural networks and think maybe a recurrent neural network can, it just needs to process things one at a time.
think much more like a linear time operation, maybe these can kind of do everything we need to do with transformers. So here's just kind of my one kind of very high level way of thinking about what a recurrent neural network is. When you look at it this way, it just looks like a streaming algorithm or low memory algorithm. And once you look at it this way, you come to the conclusion that, well, for even really basic tasks like the induction heads task, the answer is no, you cannot even do like the induction heads task unless the memory is huge, it's growing with n. So maybe this is the picture for recurrent neural networks. So unfortunately, this doesn't say that that recurrent neural networks cannot solve the problem. Maybe you can kind of create a memory state that's linear size, but just update it very efficiently. I think that's kind of an interesting open question. For the kind of this kind of multi-step reasoning tasks, there are other lower bounds that we're able to show using really nice work about this pointer chasing problem by Asadi and N. For many other kind of attempts that people have made to speed up or get around the quadratic costs and self-attention, at least for this multi-step reasoning problem, it seems like the sequential cost really needs to grow with k rather than log k that we were able to do in a transformer, or the size in some way has to be enormous, growing with n. Good. Let me just end and recap with some open problems. So I kind of first talked about the role of depth in transformers, and especially within this in-context learning problem and induction heads. The induction heads mechanism seems rather natural, and I think it's kind of easy to imagine how it might be used. And people, in fact, shown how it can be used or is used in existing language models. But I don't know about this function composition mechanism. I think that's kind of an open question, whether this is kind of an important feature of transformers. And there's some work on how you might learn these induction heads. Alberto has done some work on this, but probably not anything about function composition. So I think this would be interesting to do. This connection between transformers and MPC, I agree, it's not, it might be kind of besides the point. Maybe there are other ways to kind of establish this lower bound for induction heads, but maybe since the success of MPC has in solving a lot of kind of practical problems, maybe this connection can be more fruitful. One thing we're noticing is that the reduction is in kind of a larger embedding dimension regime, which is not clear if this is like the right regime for thinking about transformers or not. But I think maybe possibly more interesting is to really characterize what is the power of this. When you think of transformer as like this communication plan for moving information between tokens, it doesn't quite match what happens in MPC, but maybe there's something we can do to understand what how powerful is that shuffle operation. And then finally, I kind of just said some bad things about other neural architectures. I don't think this is really bad news. It just kind of points to where the directions in which you should be probing, and to see how you get around these limitations. Because I don't see as a foregone conclusion that these other architectures are doomed. It's just a matter of kind of being able to subvert the limitations that's pointed out in these theoretical results. Okay, that's all I wanted to say. Thank you very much.
Pause for the break.
I just wanted to follow up. So in MapReduce, the shuffle operation is very deterministic. Like all the tuples with the same key goes to the same reducer, the values are aggregated, like very deterministic. Whereas transformer has also query, right? So it can do that, but it can do even further in fields.
Yeah, so in a transformer, you can think of it, everyone talks to everyone. Also in a deterministic way. In this softmax, you do these query key inner products, and then everyone talks to everyone. So that's why the relationship is not quite right, but you can at least simulate what MPC protocol or MapReduce protocols do in the softmax attention. But vice versa, it requires this extra thing that Jonah pointed out.
The communication graph in MapReduce Shuffle is not fixed. It depends on the keys.
Yeah, it depends on
But it's a deterministic function of what the keys and
Oh,
that what you're saying, I think.
Isn't that true for any particular green transformer then as well? Sorry, like that's true for any particular green transformer too, right? Or I'm just understanding the distinction between
I mean, the computation graph technically is just a complete graph in the transformer. Like every token talks to every other token. But,
So really great talk. I'm curious about one thing. Since you have these explicit mappings, right? People have these approximate ways of doing attention that avoid the quadratic cost, by doing projections and so on. And it's known that those break if the magnitude of the inner products get unboundedly large. That's one of the ways they break. So I'm really curious, in your constructions, do you see that construction itself breaking, moving to very large dynamic ranges of the inner products?
yeah, so
Or they break a different way?
so we ourselves don't have any constructions based on the standard self-attention that require super large magnitude coefficients. I think with those results, I think maybe one you're referring to is talking about arbitrary self-attention and whether you can approximate that in sub-quadratic time. So that already is some limitation of these approximate self-attention mechanisms. Whether it's important for like specific tasks, like the induction heads task or something, is maybe less clear.
Okay, so it might be a different thing that you're.
Yeah, maybe something else that just works well for those tasks and not all self-attention heads.
Okay, so we can thank Daniel again, and we can take the questions to the break. We are a bit late, but we should be back by 10:40 to start the next talk. Thank you.